Otherwise,
yeah, why not?
something.
Yeah, we said no. We said quarter of. Yeah, we have 2 minutes. No, I mean,
Okay.
and we'll take this 2 minutes from your time.
Actually, he's right. It is quarter to.
Yeah. Okay. So yeah. Well.
Okay. So I will try use notation that everybody will understand. Maybe I'll try to be a little more explicit than John. I think my lecture actually, in a sense, intersects the previous two, so maybe it'll help. And it's actually, I'm surprised how many. I didn't expect many people here, so maybe I prepared the wrong lecture. But let's continue. So, what I want to discuss in this lecture, and what's the randomness issue from arithmetic, which is one of my favorite topics, is the following function. It's called the Mobius function. It's the inclusion-exclusion function, and it's at an integer n, simply -1 to the number of prime factors that n has. If n is square-free, has got distinct primes, and if it's not square-free, then the number's 0. This function carries information about primes. It carries many problems can be reformulated in it, in terms of it. And I want to discuss what Mobius is correlated with. So let's discuss it in the following language. Suppose I take the sum n up to n of mu of n, and capital N here is going to get to be large. So, and I normalize, I divide by n. So this is clearly at most 1, because mu is at most 1. And I don't like this notation, little o1, but I guess everybody uses it. So this goes to 0. That is well known to be equivalent to the prime number theorem. So that's not a triviality by itself, but it's true and known for many, many years, and it's elementarily equivalent to the prime number theorem. In terms of correlations and these kind of functions that I think have been discussed a little bit earlier in trying to detect biases and correlations, this would be, I'm thinking of mu of n times 1. Mu doesn't correlate with a constant function. That's a way of stating the prime number theorem. You could take a sum on progressions. So you take what's called a multiplicative character. If you don't like that, that's a character which has some period q, so that we could just replace this by some n congruent to a modulo q, n up to capital N, where q is fixed. And the same is true, that the theorem, I am making a big mistake here. I'm standing in front of this, right? I should step back. I once, when these, you see, I'm quite old. I'm now beginning to sound like Simoretti, who starts explaining to how he's old. That's a bad sign. But the first time I ever saw anybody use one of these overheads was Steve Smale, and this was just come out, and he gave his whole lecture on his shirt. But every time he turned around, it was very good, and then he stepped in front of it, gave it on his shirt. He had no clue he was lecturing on his shirt. Everybody was very polite. So please shout if I'm lecturing on my shirt. Maybe I'll step back here. No, but he had this vest underneath. So the fact that mu doesn't correlate against a character or on progressions is essentially what's called Dirichlet's theorem about primes in progressions. I'll discuss a little bit about primes in a second. Right. Yep. And there's a more sophisticated version of this. There are other functions here which are very subtle, which are Fourier coefficients of L functions, which generalize these guys, all of which are known to have this property. And they're all coming from a theory, the theory of L functions, just like the prime number theorem does, comes from the zeta function. And I'm going to not be interested in those functions, but they are the hardest, as you'll see in a second. Somehow, in all these features, there's going to be a structured part, just like if you listen to Green and Tau talk, they'll always, or Simoretti's theorem, there's a structured part and a random part. The structured part is controlled by these kind of things, automorphic forms, and we do know enough about that to just get this little o. If you're interested in the truth here, in other words, how big is this sum really, it should cancel to square root, not better. So it's very important for later that these things don't cancel more than square root. And that would be an issue of understanding not just the leading term here, just this correlation, but how well they correlate. And there, things can be much more subtle. And this GRH is called the grand Riemann hypothesis, is simply equivalent to these statements. So we don't have techniques to estimate that effectively, as I think you all know. All right, so what this lecture is about is to say what correlates with Mobius. So let's take other functions, Fn. Now I want to show how I'm willing to construct this, but since they are complexity theorists here, maybe they have a much better setting in which to formulate this kind of question. I'm going to stick to this for the time being. So suppose this does not correlate. Suppose that for some reason f, so this is a plus and minus at random, f is supposed to be bounded here, and suppose f knows to be 1 more often than -1 so as to make that big. So in other words, f knows about mu. If we can find some means of finding such an f where f can be computed easily or is going to be generated by some simple-minded idea, that would be fantastic, because I would drop everything I'm doing. I'll go study that system and see what this f is. If it's not defined by mu itself, if it's tautological, it's of no interest. So what kind of f's do I want to allow there? I just want to point out in terms of rates, some years ago, Lua, Ivanic, and myself showed that there can be quite deep and unexpected correlation. So this square root philosophy is something you must be very careful of. If mu and were really random, everything's square root, it's actually false. You can have correlations that are not sort of obvious, rather deep, but not at the level of the leading term, but bigger than the square root. So you must be very careful with square root. By exponent of actually 3/4. So 10 to the 3/4 is our main example, where it's related to something of another type. So let me just say we stick to leading terms. All right. And in this lecture, as in the title of my lecture, I'm going to describe this for substitution sequences. I'll tell you why I got into this in a moment, but I think the substitution sequence is very natural from many angles, especially the angles of two of the previous talks. So how am I going to generate this sequence of numbers Fn? It's supposed to be simple. So let's see how simple this really is. So let's take a space X, which is a finite measure space, and this is terrible. That's supposed to be a nu. I did change it to nu. Mu is mu. It's Mobius. Nu is the measure on the measure space. So, but you always make mu a measure also. Anyway, so I take a measure space X nu and a transformation from X to X. Pretend it's 1 to 1. It doesn't have to be, and it preserves measure. And the only invariant measure which is absolutely continuous respect to nu is nu itself, so that's ergodic. So you don't need to assume ergodic in what I'm doing, but things break down into ergodic pieces. I also want X to be a topological space. I can talk about continuous functions. I won't be looking at anything fancier than a continuous function. And I'm going to make my sequence to be f at t to the n x. So I first fix x, a point in x, and then I just iteratively substitute, and I learned from Eisenman, a colleague of mine at the university in physics, he calls these substitution sequences, and they are easy to generate if you have your transformation and you have your space. But of course, there's x here as well. Keep that in mind. And now let's ask whether Fn correlates, knows about, or in some class, Mobius. X so far is anything. Now you see, Bergan has a lot of theorems, and I actually put his name down with this theorem. I should have erased it after this morning. Any theorem that has no name is due to Bergan. Now, actually, when I look at the literature, I actually see that you didn't quite prove it. This guy used your methods to prove it, as far as I can see. I didn't see it in your paper. In any event, in a beautiful series of papers, Bergan generalized the Birkhoff-ergodic theorem. The Birkhoff-ergodic theorem is a statement about the averages of an L1 function, or let's say an L2 function for simplicity here. But here I'm only going to look at continuous functions, as I said. That should converge to the average of the function. So, but I'm correlating against mu. Here you'll see on primes in a second. Anyway, the Birkhoff theorem is just saying that 1 over n, this times applied to Fn t to the nx for almost every x relative to the measure converges to the integral of f. And what Bergan did was generalize the standard Birkhoff theorem to arithmetical subsets in the exponent, like progressions, like powers, and these methods can be used to get it on primes and to do it against Mobius. So if the question that you ask is for almost all x, here's the answer. There's nothing more to say. So you might say, I say to Bergen, well, let's use your theorem. Is this useful? Well, the trouble with almost all is that's random. You've built the randomness in there. And hence, it's not particularly useful if you're hoping to understand something more concrete about primes or something like that.
Constant function for it.
Yes?
The prime number theorem.
That's the prime. Of course, in the proof here, Bergen will have to use L functions on the constant function, yes. So the rate of convergence here is not, when f is constant, is only going to be as good as the prime number theorem, which is a very slow rate in its present technology. Yes, correct. And this and that are very closely related. So what happens here is that if you take the values, you take this, the substitution sequence at primes, you're getting that the Birkhoff-Ergodic theorem is true when you go only over primes, which is a rather nice theorem. And that's true for almost all x. It doesn't.
This is a more complicated story, but
Okay.
about the convergence rate.
I don't give convergence rates.
Where you get control on the variation.
Oh, yeah, but I'm not. This statement.
Tell you later.
Okay. That's for almost all x. Now, if the transformation is complicated, you could ask, is it true for all x? And the answer is, it won't be true for all x. And let me show you that we can make a correlation. It's trivial. Suppose I make my transformation x goes to 2x on the interval 0, 1. So I'm looking at arithmetic modulo 1, just the fractional parts of numbers. This is measure preserving. It's 2 to 1. So his theorem will apply. For almost all x, these will be true. But I can make I can choose my x naught cunningly so it knows about Mobius by taking f to be sort of the first half of the interval. Then it's picking up just the dyadic expansion of a number x. And if I choose x naught to have dyadic expansion which knows about mu of n, which I can do because there are a lot of real numbers, so I just write down its dyadic expansion, then this will correlate. So there will be an x naught in this dynamical system for which this is not true. He's showing it's true for almost all x, but there's this x naught where it's bad. Of course, if you gave me another definition of x naught, I will put everything down and work with that x naught. I don't know what that real number is. That's tautology. There exists a real number, but it's defined backwards in terms of Mobius. And that's true in any complicated system. Yeah?
So is it important here that you do with prime or any pseudo-random sequence to do that?
In Bergen's theorem, it's very general. For almost all x, it's very general. He can do polynomials.
Sequences which are not good for that.
Yes, yes.
It's not enough to have a pseudo.
No, I don't know what a pseudo-random, but it doesn't have to be primes. It does not have to be primes. In fact, he never proves it for primes. As far as I can see in the literature. But certainly his methods were used.
No, it was done independently.
Did you write a paper on it? Okay. It's not on MathSciNet. See, I've learned how to use MathSciNet. Okay. So the interest is, suppose the dynamics are rigid. So suppose that there's a structure. So the trouble with the doubling map or an no-self map or anything really complicated is closures of orbits can be sets with very complicated Hausdorff dimension. I want to look at much more simple at some level dynamics, but still very rich. So the word that we use here, or I'll use, is called rigid dynamics, and I'm going to give you the most interesting case of this, and we're going to talk about its generalization quickly. Suppose a transformation, instead of being doubling, is rotation. So that I'm taking x to x plus n alpha, where you think of alpha as irrational. So it's rotation of a circle. This doesn't have the kind of randomness. It's not mixing. But an orbit is either dense. If alpha is irrational, it's dense. Or the orbit is finite. The kind of f's are spanned by exponentials. This is the same as Jean's notation, e to the 2 pi I. And if I can work out what's happening with f of this type, then I can understand a general continuous function. And in this setting, there is a major, major achievement of Vinogradov in his proof that every odd number is a sum of 3 primes. He introduced a fundamental technique of correlation, which I'll return to in a minute and explain it schematically in a moment. And that was quickly picked up by Davenport. And in this, they prove that for, you can put an x in here, it'll just factor out in a harmless way. For any, so let me just look at this. uniformly in alpha, this is going to cancel. So this function, which I'm going to call a quasi-periodic function. The question is, what kind of fn's can't, well, if a periodic function correlated with mu, we'd understand mu. If a quasi-periodic function, which is this with alpha irrational, and on a torus, the obvious generalization, if that correlated with mu, then of course we'd understand mu too. These are very simple functions, and these are random. The randomness in that is what I'm interested in. I keep on saying that. Okay, so in this proof, they have asked, the rate here is very hard. You can't get a uniform rate, but I want to point out something. So if alpha is very close to a rational number a lot of the time, then you're going to have to use arguments which were correlating against progressions, and those are the hardest ones to deal with. What Vinogradov understood, that is, if the function fn is random in a certain sense, then you can actually get a power saving in such a sum. In other words, if, say, alpha here is root 2, then you can actually get a power saving here, I think, of about n to the 7/8. You can get a power saving. On the harder problem, if you got the power saving against 1, if you got 7/8, I'll prove Riemann next day. You'll just show me your proof. I'm sure it'll go. So it's an interesting point that the randomness, when it works, gives you a better result. The randomness is a technique of Vinogradov that I'll return to and say a few words about. What? There's no, if this is random, there's no input. But to state any theorem of the type that I'm about to state here, that a consequence of this is, as you all know, n alpha mod 1 is equidistributed and dense if alpha is irrational. The same is true for p alpha mod 1 if you go over primes. These are immediate consequences of Vinogradov's work. So the simplest kind of thing to worry about correlation against is a quasi-periodic function, and that was understood by Vinogradov, and is still perhaps the main deep insight. The fact that he's going to look at what are called bilinear forms, certain quadratic correlations. This was generalized to the torus easily, but we heard about Green-Tau's theorem, and in fact, there was Green talking here 1 year ago exactly on this theorem that I'm about to state. That irked me enough to start thinking about this problem, as I'll explain to you, only because of his terminology, and I complained to him at the end about his terminology. He kept on talking about Redness Theorem, and what he was talking about was what I'm about to show you here. And that is the following. So Green and Tau, I'll say a word about this, generalized this Vinogradov method, I'll say a few words about that too, to a null manifold. That's a remarkable generalization. It's not that difficult, but it's 2 of a series of 5 papers that they're writing. It's the most recent 2, and that's what they've been lecturing in the last year. A null manifold, I'll explain why in a minute they're interested in that. A null manifold is something that's very close to a torus. It's got a finite derived series, and this is what you should be thinking of, the Heisenberg manifold. You take upper triangular matrices, you take them with real, so instead of taking R over Z or R to the N over Z to the N, you take these matrices with real coefficients, you divide by the matrices with integer coefficients, you get a compact manifold, which is kind of a twisted torus. It's a null manifold. And in this context, they generalize Vinogradov's methods quite nicely to prove that mu doesn't correlate against any null sequence. A null sequence is simply a function on this null manifold, which is evaluated. They actually have to make it slightly more complicated in connection with the previous talk in order to push through what's called the transference principle. In any event, this is the main theorem proved by Vinogradov's methods, that mu doesn't correlate against a null sequence. So a null sequence is still very structured. The closure of any orbit is a null submanifold. Redness theorem is a fantastic generalization. In this case, this was not long before Ratner, but they kept on calling this Redness theorem about the equidistribution of an element and its powers being rigid in a null manifold. That's what bothered me when he kept on calling it Redness theorem. So I went to him afterwards. Yeah.
That's for every U or for
Any f, any x, mu cannot correlate against a null sequence. There is no sequence on a null manifold of what's u here? U is any element in the n.
any
Sorry.
element.
any element. I mean, if it's identity, then this is constant. If it moves, then it may have a periodic orbit, then it's Dirichlet's theorem. It may have a circle as a closure, then it's Vinogradov's theorem. It may have a torus as a closure, then it's still Vinogradov's theorem. And then in general, they do it by induction with a lower derived series. So it's a quite nice theorem. And they didn't get to this just for fun, I should say. This is part of their linear equations in primes program. Call it a program because a program often means that somebody's stuck. And whether they're stuck or not, I can't get to the bottom because they'll never give the big paper has, yes, we can do it, yes, we can't do it. Anyway, the first four papers are written. And they are, the ultimate theorem will be really impressive, far more impressive than progressions, long progressions in primes. It's solving any linear equations as long as there are two more variables than unknowns, homogeneous or not, local to global principle for linear equations that you can solve. That would be a truly outstanding, complete piece of work. And this null manifold enters into the analysis beautifully through the work of Host and Krah, Furstenberg, and Weiss. They understood that what you should replace the circle by in this Simoretti type theorems is a null manifold. So the null manifold is the only thing they're interested in actually, and they've done it. The techniques, however, to do this correlation in the null manifold are reasonably standard. Okay. So that was his lecture here last year, very nice lecture. The only difference is I'm saying a null manifold and not Ratner. Okay, so I just said this. So here's the consequence of their work, which is itself really fundamental. That if you take a null manifold, you take U, any element in NR, that's what we asked, take any x, doesn't matter what x is, and you take these points, they become dense in the closure of the full orbit. Another way of saying it is the primes are as rich as the integers. They are as dense as the integers. They don't, this system, and that's the same as mu not correlating against anybody in this language. The primes are as rich, they all have the same closure. The closure of this, in the case of a circle, is trivial. It's either finite or the full circle. In the case of a torus, it's called Kroneker's theorem. These are easy theorems. In the case of a null manifold, the closure, this Ratner theorem, is easy. Yeah?
Is the same theorem easier to prove if you replace primes by pseudo-primes?
Yes, much easier.
And then can't you derive it from the transverse principle?
No.
I was talking about now?
Not that I know. No, this requires, no. Let me, No, this is a very important point. The theorem about linear equation primes is far deeper than combinatorics. Let me explain this point. It's a local to global principle. There is no theorem that I know of in the sets of density which say you can solve linear equations in a set of positive density. They only say you can solve linear equations. The linear equation is x1 minus x2 equals x2 minus x3, a progression. Or some generalizations of that, multi-dimensional ones called the Hale-Jewett theorem, but they all have the very important feature that there's no local congruence obstruction to solving them. So they have to be homogeneous, for example. Their new theory is going to deal with inhomogeneous equations and any set of equations, as long as the number of variables is two more than the number of equations. And in that case, they're proving a local to global principle, which does not only involve this transfer principle. This is the part that involves a number theory that's much deeper than, they didn't need any number theory before. Before, they only needed the fact that there are infinitely many primes.
The linear equations are homogeneous?
No,
Or
any linear equation.
so then, for example, it's not true that any constant density of the prime
Correct.
is a solution, right?
Correct. They are local. There's a local.
Third of the primes, then maybe there will be no solution.
Right. So there's a local obstruction that you have to pass, and their theorem says once you pass a local obstruction, you can solve linear equations in primes.
But this is only the very end of the story.
They haven't proved that. They've proved it with their new case beyond Vinogradov. They have one new case beyond Vinogradov, and that's two equations in four unknowns, inhomogeneous. And that's because they can do this inverse Gauss for U2, but they don't know how to do it in
Is there
general.
an example which is true for the primes?
I didn't come here to talk on their work, but anyway.
It's
What?
not true for a subset of half of the primes, or it's not true for a subset of 10% of the primes?
Yeah, if you're going to put that subset, you have to put a congruence condition, then you build it into the local congruence.
I see it from the general, but you said that you don't know the general.
Not if it's inhomogeneous. There's no there's no Semiretti theorem that I know that allows congruences.
You can make counterexamples.
Yeah, you just take all the primes that are 1 modulo 3.
Yes, no, that's a local congruence obstruction. Okay. So at the end of the lecture, I had a discussion with Green, and I said, you write G mod gamma. I live G mod gamma. But for me, G is semi-simple, and for you, G is nilpotent. And let me clarify that for Ratner, the depth of Ratner's work is this rigidity in the semi-simple context. So obviously, everything you're stating should be true in that context, and we agreed. And Ubis, who was here last year, a Fulbright fella, and I decided to try see what you can say. And I must say that in this case, you will see we have a very modest understanding. It's much, much harder, and I want to explain why and what we can prove. But again, it's going to be a very simple conjecture. So in terms of posing problems, I don't give you more than one problem, just one problem. I'll state it right now. So instead of having X is now just going to be any, I'm going to give you an example in a moment, the only example we study, and it's got most of the difficulties in it. But the nice thing here is that this should be true completely generally. So instead of having n over gamma or a torus, we're going to have G a connected Lie group and gamma a discrete subgroup such that this volume is finite, the quotient. That's a setting of Ratner. We take an element U to make sure we don't have too complicated dynamics. We need a rigid dynamics, as I explained that if we had doubling, we were in trouble. We want to assume, and this is the heart of Ratner's work, that the transformation U, whose powers I'm going to look at, is add G unipotent. That means that when it acts linearly, the eigenvalues, this matrix is in upper triangular form and 1's down the diagonal. I'll show you in an example in a minute. That's the key condition. Now there's something this isn't automatic in a null manifold, because, well, at least in the example I gave you, it was upper triangular. And the nice thing, and this is the heart of why this is much better behaved, is when you take a power of a unipotent matrix, it's a polynomial function. The entries are polynomial functions. While if you take a power of a genuinely semi-simple element, like A inverse, then you get exponential behavior, and that's too complicated for us to understand.
So you would have to make a conjecture in generality.
It's false. Yeah, that's what the doubling shows, and it's false.
No, but if you drop hyperbolicity, if you assume that the system doesn't have any hyperbolicity.
No, I wouldn't make it.
You wouldn't have
Not yet, no. But I am actually very interested in the class of how to formulate the problem of mu doesn't correlate properly. And this is one way that's related to homogeneous dynamics. If you don't like it, you probably should leave now, because the rest is about one example in this case and to explain what are the issues. So I mentioned here Redness theory. This is a remarkable piece of work.
Could you say what the conjecture was?
I'm going to state in a minute. Let me. Rigid dynamics. So Ratner showed that if you take this setting that I just have here, and I take a power of an element U, and I look at U to the n, and I look in the space, and I look at its closure can't be complicated. It has to come from a subgroup, basically. It's what's called homogeneous. So the closure can't be a fractal set. It's very rigid, and even the points on the integers are equidistributed in the closure. Now, there's something, and we've seen this alluded to before, the ergodic theory, the softest ergodic theorem, especially those of Furstenberg, often only just give you existence. That's because in ergodic theory, you often argue by taking a limit and then classifying the limit, and that gives you for free some limit exists without knowing any rates or anything. Ratner's work is not known to be effective. It's perhaps the most important unsolved problem there, and this, as you will see, demands this. So let me make the conjecture. Here's the conjecture. Conjecture 2 is a folklore conjecture. Conjecture 1 is stated here. I guess you could add Green, Ubis, and myself, because we quickly came with this conjecture when he was here. So let U be in G is above, f a continuous function on this quotient space X. I'm going to give you an example of an X, so just bear with me. But the conjecture is that mu doesn't correlate against any continuous function on the powers against mu. In other words, it doesn't correlate. I'll call this a Redness sequence to indicate that we are in a general case, in particular a semi-simple case.
But the potency is not essential.
I think, well, if it's not, if your element,
As long as you don't have exponents, it should be true.
It may be, yeah. So the difference between unipotent and no exponents is is going to be that the eigenvalues are modulus 1. In that I think you're right. I think that's probably true what you say. But I'm going to assume unipotent in stating this. It's bold, but it's probably true, and it's consistent with this, which is a folklore conjecture. So I didn't know about this until I started recently to look at the literature, and it's in a conference a few years ago written up as an interesting problem. So it seems like it's born from Dani, Mogulis, Shah. And it's the following statement, precisely as before, that if you're in the setting of this G mod gamma, that if you go on primes, u to the p times a point, you will be as rich in this rigid dynamics as when you go over integers. These are closely related. This is harder. This is this should give you a complete understanding. This can often be proved by less information. So the first thing is you want to know, is the orbit, when you just go over prime numbers, dense? That's sort of the standard problem you always ask. Is it as dense as the integers? So it should be dense in the closure of the full orbit. And then you can ask more, is it equidistributed with respect to the unique homogeneous measure on that space when you order these primes by their size? So that's our conjecture. Yeah.
I'll ask the same question I asked the slide before. If you replace in either of these conjectures n not by primes but by pseudo primes, then
I can't prove it in general. In the case I'm about to tell you, I know how to prove it. Absolutely.
and you rule out transference principle in this setting.
For pseudo primes with a fixed number of factors, yes, I will show you what it is. I will show you the big difference in what Vinogradov's idea is in a second, and that's critical. Okay, so that's my problem. That Mobius doesn't correlate. Now, of course, if it were false, I'd be much more excited. So I win either way, as long as you solve it. It's not like a guy who says, a guy who presents a proof of Riemann to the annals both, and then sends a disproof the next day, and then says, look, one of them must be right, you decide and publish. I need to know which is correct, at least one of them is correct. And I need to know that you know what's going on. So in the conjecture, if for some reason a Redness sequence wanted to correlate against Mobius, or anything structured that you might give me a better, more general definition, for which you could compute quickly in that class, then this would give us a way to compute mu of n and factor primes, I'm sure, in anything. So if you think that factoring's hard, then you shouldn't think that Mobius can't correlate against anything in some class. And that's a first step to try and understand this. That's my connection to computing. What I'm saying is if you were able to tell me what mu of n is quickly, or even with some positive probability, then you're starting to tell me something about mu of n quick. So if f is computable quickly, as it is in this case, f is easily computable in this G mod gamma. Sorry?
Logarithmic in n.
Yeah, it's just you're iterating on the inside. You write down.
It's like repeated squaring or something.
Yeah, it's very quick. So if there was a correlation, yeah, you would be telling me Mobius isn't as complicated as I thought. So it better not correlate.
But if the proof would be
Okay, I don't have a reduction. It's a philosophy. Come on. This program, philosophy means you have no idea what you're talking about. Program means you're stuck. So when they talk about some philosophies of mine, forget it. Okay, this is the mother of all semi-simple groups, SL2R. The discrete group is SL2Z. The situation is essentially as complicated as it ever will get. And I'll explain why in a second. My unipotent transformation is that I'll choose. The unipotent flow that goes with that's just a flow from which this is a time one map, is called the horocycle flow, and it's doing the following. So firstly, if I make this quotient, this is three-dimensional. So this x is three-dimensional, but I can't draw in 3 dimensions. I'll draw it in 2 dimensions, and then I'll just ignore the angles. So this one way of thinking of this is it's the set of points and directions in the upper half plane. So I just put the points. Then this flow, this part here is the flow that you get by taking a circle. This is what's called horocycle. It's a circle which is tangent to the infinity in hyperbolic geometry, and you move arc length. You decide So if I give you a point and a direction, there's a unique circle tangent in infinity like that, where this is pointing inwards, and then I flow with some orientation, arc length, to a new point. That's what this is doing. And then you have to think of doing that all in reducing modulo this thing here. So you're not reducing mod z, you're reducing mod SL to z, and that's what makes the Redness theory, the dynamics, much more difficult. And it also makes the functions that live on these space much more interesting. They carry much more information. For example, the theory of automorphic functions are functions which are periodic in the sense and satisfy some differential equation. While the theory of automorphic functions on a torus or on a circle is just e to the 2 pi I x. And that's a function which is not uninteresting, but rather simple. So here, anytime you try to study something like this, you face much more difficult problems. And that's why Redness theorem is a deep and important theorem. So Redness applies here. Actually, this was known in this case. And I want to point out that this has the difficulties, many difficulties, that we should be aware of. Firstly, not every orbit is dense. So there is Redness theory, which says that every orbit's closure has to be structured. In this case, this theorem is due to Dany that I'm about to state. It's pre-Redness. So let me give you a periodic closed horocycle in the quotient. Suppose I take the horizontal. This is a picture of the upper plane above here. Suppose I take this as my horocycle, meaning the point at infinity is the boundary point, so that the horocycle becomes a horizontal line. The arrow is pointing towards infinity is there, and I flow along this horocycle. If I move from there with that tangent vector to here, length 1, that's the same as this transformation, which is in SL to Z, means this vector will, this point in the 3-dimensional space will be that point, and this will be a closed horocycle. So for each of these horizontal lines, and these are the only closed horocycles, I get this infinite family of closed horocycles with longer and longer period. They're going to have different closures to other points, almost all points. The ergodic theory is easy. As we saw, almost all point behavior is not hard. By the way, these kind of flows, like the rotation, like the null manifold case, all these have zero entropy. So the dynamics at that level is simple. They all have zero entropy, but these are mixing of all orders, while the circle rotation is not mixing. So they are dynamically richer, but they don't have positive entropy, since I know you guys love entropy. Okay, so that's the case in which we can make a lot of progress, but unfortunately we can't solve it even there. So I just stated Dany's theorem. And now I can state what we can prove, and then I want to explain a bit of Vinogradov. So Dany's theorem, in this case, there are 3 possibilities for the orbit. I've already stated that. Either the orbit's periodic, you come back to where yourself after a finite number of steps, or you like a rotation of a circle, meaning the closure is a closed horocycle. The closure is topologically a circle. And if you're not in these 2 cases, you are in the 3rd case, that's a trichotomy, you are dense. And this is the hard case. So if I want to now ask our conjecture about correlating of functions in a periodic case, that's Dirichlet's theorem. In this case, it's Vinogradov's theorem. And in this case, it's the first and basic new hard case. And there we are unfortunately unable to prove, so I'm now going to answer one of Avi's questions. We're going to prove something about the possible equidistribution. It's slightly weaker than what I would love. So let me state the theorem. Let me take point masses at the orbit at primes, and then normalize it by pi of n is a number of primes up to n. So this is a probability measure on SL to R over SL to Z, the space I was showing you. And it depends on x, starting at a generic point, by which I mean case 3, the hard case. And then the question is, the conjecture says this should converge to the invariant measure on the space x, which is just the Haar measure, the standard measure. So I don't know how to prove that. What we can prove is that any limit is absolutely continuous, meaning it's the measure that this will give to any set is at most 100 times the set. So I only have an upper bound here. On the other hand, I didn't write this down. Our method will give, in this case, that if you pass from, what did you call them? Almost primes?
Yeah.
We can prove the theorem if you allow probably, this 100 is connected with that, maybe 100 almost prime. Then we will have a proof. Okay, you'll see why when I give a hint at what goes into this. So that, and the mass doesn't escape. So this is quite strong. Now, usually when you get to a position like this in the ergodic theory, you're done. Because if your measure is absolutely continuous and it's invariant under U, then it's ergodic and there's only one such measure and you're done. So the minute your measure is not very singular, you're done. And this says the measure is not only not singular, but it's done. The trouble is, because you're summing on a weird sequence like that, I don't know the measure's invariant under the shift, which if I form the same thing, sum n up to n, 1 over n, it's trivially invariant under the shift by amenability of z, if you want to call it that. So that's this doesn't finish the proof, which it normally does in this kind of subject, and that's because we're on primes here. But nevertheless, this is still very strong, and it has many applications. And I don't want to, I realize I shouldn't, well, let me state a case where we can get a lower bound and then explain. So I won't explain the applications, which do show that while the set is not dense, it's very big, immediate consequence of that. I want to explain a case where we can handle this, and since it uses expanders, I thought I'd put it in. And it's still conditional because these expanders have to be the best in the world. So that I like too. So instead of taking my starting point to be a generic point as in condition 3, let me take the starting point to actually vary with n. So I will take a periodic point for the flow of period n, which if you check this point is like that. That's the point I was showing you earlier. Okay, so if I iterate u on this n times, I'll get back to where I start. And I'm going to make the measure, which is, instead of summing j up to n, which will just be all the points in the period, I'm going to sum over the primes. So I'm making this measure. The main difference here is the starting point depends on n also. If you want to understand the complete Mobius problem, does Mobius correlate against a function? Yeah, you'll have to handle every starting point. If the starting point is periodic of small period, it will reduce to Vinogradov very immediately. This is sort of the longest it can be and still structured. So unfortunately, we don't know how to handle the general starting point uniformly, but these points we can handle. And the reason we can handle them is we can give a lower bound here, which I'll explain in a second, and prove they're dense. However, and you don't need to know what this is, but everybody will have a feel for this, you need to show that certain graphs are expanders in the Alon-Bopana optimal sense, which we don't know for this setting. We only know very good approximations to it that I've spent many years working on, and unfortunately these very good approximations are not enough to complete this theorem, just miss. We need the full force of what's called Selberg's eigenvalue quarter conjecture in the p-adic case. And that's a graph, certain graphs that you make out of this construction need to be optimal expanders, meaning they're 2 root k minus 1, in this case 2 root p. So with that standard assumption, which has nothing to do with prime numbers, but which I believe in the end is a very critical ingredient in trying to understand the deeper things about primes, we can get what we want. What we want is the next slide, and then I'll say a word about how such things are proved. So we get a lower bound. For primes, not for almost primes. So this is the hard thing. So now I don't get the asymptotics. I still don't get that Mobius is not correlated, because that was a constant. This is off by a constant, so this is an approximation coming from Vinogradov's methods. But the lower bound tells me I'm dense and everything else. I won't give there's a, I think, quite nice application to Diophantine problem of Linux. I'll skip that. I want to say in the next I have 3 minutes, I think. I want to say something about Vinogradov's method, so I'll skip all the applications and tell you what's at the heart of this and why this is hard. So let me clarify why this is very difficult and why it was doable in the circle and why it was doable by Green and Tau. And that is that Redness Theorem is not known to be effective in it. There's no effective proof of it, meaning you prove abstractly a certain limit exists, you get no rates, and if you want to use any techniques to go from progressions to primes, you need rates. To get almost primes, you need some expansion, kind of uniform rate. To get primes, you need something much more difficult. That's what I want to point out. And in the torus, what happens is when you want to get these bilinear sums that I'm going to write down, you take the product of the torus with itself, and so you get into a position which is the same as what you were dealing before with. Here, you might start off with a situation where you have an effective equidistribution, which is one of the big things we prove here. But when you want to do these bilinear sums, these correlations, you have to face Ratner in the product, and that is very difficult. So the kind of sums you need to control, let me just explain, there's a parenthesis missing there, see, are sums on progressions. So it's like Jean was talking about, you need an equidistribution on on a progression where the progression length is getting quite big relative to n, and you need to have some cancellation from the homogeneous expected, there's a parenthesis missing here, and you only need this on average. So these are called type 1 sums, and these type 1 sums you would get from an effective Ratner if it was sufficiently handsome. And we have that in the case we're discussing. And that's why we get to understand these sums, which are enough to give upper bound sieves, which is what the first theorem uses, and it's enough to get almost primes, which I didn't put on there. But what Vinogradov's big idea, how to understand Mobius without understanding Mobius, is to estimate the norm of some matrix in some estimates. It's a version of Cauchy-Schwarz, but where there's some beef inside there. And that is you need to be able to get cancellation over. Now notice what we have here. We have a starting point. This is the case where we can prove it. We have a starting point there where D1 is quite big, D2 are quite big, and I have, this is the type 1 sum, but I now multiply it by f. I could change this to another f, and I could polarize this and make this another point. So I need these quadratic sums, I call bilinear sums, and I need to get a non-trivial cancellation on that sum for any function continuous of the type we discussed. In this case, I'm assuming the integral of f is 0 in this example.
This will be proved separately for each u, or you can...
No, u is the one I wrote down, and you can scale that in. U is fixed. But what is not fixed is the power of u here. The d's are very important. That's a level of distribution. Okay, and this we can only prove with the best expansion property, which is not proven. That's why I had to assume that conjecture. We're just missing, and what you need is this, and Vinogradov's idea was if you control this and that, then you can get down to primes, and that's how he controlled this just on a torus, and how green and tau. So in green tau, this is just, say on a torus, this is just exponentials, and the sum when you multiply two exponentials, just a third exponential, and it's no different to what you were dealing before. So the type 1 and type 2 sum are really no different. So this is really a correlation sum that you need to input, and this correlation sum in a Ratner type situation is not known. So Ratner will tell you that this converges to some algebraic measure applied to F1, F2 because it's on the product, but it will give you no rate, and that's just not good enough.
You really need the epsilon?
No, logs are enough. Log to an arbitrary power is enough there. Yeah, that's a subtle and important point. Okay, and so our proof first needs to effectivize Dany so that you get rates, and that we've done, and it's highly non-trivial because the quotient's not compact. And then this comes from a much fancier theory. It's a theory that Ivanich and I and many others after us have developed called shifted convolution, which is a quadratic sum, which the version of which we need is due to Blomer, which is stronger than what I had previously derived, and only using his and the full Ramanujan do we get the parameters to fit so that we eventually get the lower bound to produce primes. So producing primes is hard in general. Thank you.
Full Ramanujan here, so you
No, you don't need it. No.
if you yeah.
So yeah, I don't need what I need. So the record we have is the trivial bound is a half the exponent. We have an exponent, Kim and I, of 7 over 64, slightly better than a ninth. You need, if I computed it correct, 12th. So, and a slight improvement of that would solve this. But I should say Kim and I used the exceptional group E8. So our well, which was supplying this, has been dried. So you'll have to find something much cleverer. And we have tightened every screw that we can see. So I never thought there would be a problem where the difference between a ninth and a 12th would be relevant. But it is at the present technology. Somebody might do something else more cleverly and get into the game earlier. Right, I'll stop there.
Some questions, Peter.
Yeah. Yeah.
Can you give some background on the Mobius function? Why is it so interesting?
Well, it does control the distribution of primes. So suppose you ask how many primes there are up to x, weighted by log of p, properly counted. And you want to understand how many primes there are in a short interval, which you can imagine is useful. Then the optimal understanding this sum of Mobius will tell you that the Riemann zeta function has no zero. The Riemann hypothesis would follow from the correct control. In terms of primality testing, it was well known that the Riemann hypothesis for these L functions implied, this is a test of Miller, not that guy, I don't think, some other Miller. But that was before the recent work of Agrawal et al., which got rid of that aspect. But it was already known. So it's a very powerful tool in counting anything like primes quantitatively, not just the main term. And that's where controlling sum of Mobius. So if you could understand Mobius from some other picture, this is everybody's dream, it's not going to come out of a substitution sequence. That's clear. But the interest here is to prove that, because that's independently interesting.
No, for sure this is not this.
Yes. Yes. Does not reduce to the no case. No.
No, you know it is not.
Yes. Yes, I can show. These sequences have correlation. They're mixing of all orders. The dynamics is seriously much deeper. Orders, mixing of all orders.